This video is about Superheterodyne AM receivers. So we all receive the AM signal from the radio devices, and the protocols which govern the spectrum is from Federal Communications Commission (FCC), and they define a certain spectrum, and that spectrum in most countries start from 560 kilohertz and it goes up to roughly 1600 kilohertz. And herein a bandwidth assigned to a given user or a given station is basically 10 kilohertz. This means that if we have a station, say S1, so the spectrum for this station is basically like this, and in this range or this bandwidth is 5 kilohertz. After transmission or modulation at say 560 kilohertz, now the overall bandwidth required would be 10 kilohertz, which would include the upper sideband and the lower sideband. So as we can say that under this scheme, if you are assigning a bandwidth of 10 kilohertz for a given station and the overall bandwidth assigned by the FCC is just over 1 megahertz, so the total number of stations, so this is bandwidth of AM divided by bandwidth of a given station. So this was roughly 1000 kilohertz, that is 1 megahertz, and bandwidth of one station is 10 kilohertz. So we are having approximately 100 such stations. This is basically the protocols or the frequency assignments for a given AM signal. Now let us see how we can transmit such kind of a signal. So over here, this is our station 1, and then this is station 2, station 5, and so on, then station 91, 100th station. Since we are dealing in AM, so we are giving a DC offset to this message signal. Baseband now would have a spike indicating a DC value, a significant DC value, right? So this would appear for all the message signals, and then we would use a local oscillator, right? So in the first station we use a local oscillator operating at 560 kilohertz, right? So this spectrum would now move to 560 like that, whereas this station would now move to 570 and so on. Now these stations can be in the form of a single broadcast station, or they can be separated geographically and spatially, but eventually in our vehicles this is the signal that we eventually get or receive, where we have the station 1 spectra, station 2, station 5, 91 and 100 and so on, right? So in between there will be some stations over here. Usually we assign few hertz in terms of guard band, so in AM, and this is basically used to avoid interference between two successive stations, right? And the use of this DC is linked with an ease in demodulation, whereby we can use an inexpensive envelope detector. So let us again focus on the received signal that we would get in an AM radio device. So this is that received signal, that is 5 AM of F. Now let us say we are interested in tuning just one particular station, and that station is at the carrier frequency of 600 kilohertz. So we are interested in a station which is at 600 kilohertz. So one obvious method is that we can use a band pass filter at this point, right? So in this way we would reject all of these stations and eventually we would have the desired station. And once we get that, we would use envelope detector followed by DC block to receive our particular station. So this is an obvious method to use a band pass filter around 600 kilohertz, and it would have a bandwidth of 10 kilohertz. So this would start from roughly 595 and 605. So this band pass filter has a bandwidth of 10 kilohertz and it has a carrier frequency of 600 kilohertz. So this solution looks very promising, but there are certain limitations which restrict us not to use this kind of a filter. So if we use such a filter, right, so this filter can be quantified by means of a quality factor, which we refer to as Q. And this Q is linked with the carrier frequency Fc and it is inversely proportional with the bandwidth. So presently we are tuning into 600 kilohertz, right? And the bandwidth is 10 kilohertz, right? So this Q factor is 60. And generating a band pass filter with such a high Q factor is quite complicated and not easy to manufacture. And such solutions would be rather expensive as well, which are undesired in low cost user radio devices. So the first limitation is a high quality factor, and the second limitation is that right now we are basically trying to tune to this station number 5, but if we want to tune to station 2 or station 1 or station X, say 91 or 100, right? So this band pass filter would be tunable filter, right? So having a filter which is having a high quality factor and on top of that it is tunable, we shall be able to tune it to 570, 560, 600 and so on. So this really complicates the circuit, so we need to find some alternate solutions for the demodulation of a given station among a number of different candidate stations. So the solution for this kind of a problem is to move into frequency shifting or heterodyning, and we would like to shift the frequencies to an intermediate frequency. So what we are trying to address here is we assign an intermediate frequency IF. In AM that intermediate frequency is at 455 kilohertz, right? And we use a band pass filter over here, right? So we have an intermediate frequency at 455 kilohertz and then we use a band pass filter at that intermediate frequency. So whichever station we need to tune into, for example previously we were interested in station 5, so we would translate this station to this intermediate frequency range, right? And then use a fixed band pass filter, right? So two stages: shift the frequency and then use fixed band pass filter with low Q. Since it is at 455, so the Q factor would be less than at 600 over here. And when we shift this, we can reject the other station and hence we can tune into the desired station. Now this brings us to this Superheterodyne AM radio receiver. Over here we have an antenna. These two blocks are basically linked with RF band pass filter and RF amplifier. So just we would hold this discussion for the time being and we'll move on towards this mixer. And this mixer uses a local oscillator which would do this heterodyning and shifting to intermediate frequency. Right, so this is done by this mixer, and then we have intermediate frequency amplification and filter. Right, so this is the gain amplifier and this is our band pass filter at intermediate frequency, and finally we would have some demodulation and some amplification on towards the speaker device. So in short, this translation in frequency in the intermediate frequency range is done by means of this local oscillator over here. And as it brings us to the point that what are the types of local oscillator and which one is a good local oscillator. So this translation of a given station to 455 kHz can be done by means of either up conversion or by means of down conversion. So in up conversion, we have omega C plus omega IF, and in down conversion, we have omega C minus omega IF. That is, over here we have cos 2 pi FC plus minus FIF t, right? So this is our narrow band. So we can either use up conversion or down conversion. Whichever we use, we would eventually get an intermediate frequency over here somehow. So we'll see how we'll get that. But first let us compare the up conversion with respect to down conversion. So in AM, we know that the frequency range is from 560 kilohertz to 1600 kilohertz, right? And we also know that our intermediate frequency is at 455 kilohertz, right? So if we add 560 with 455, so we have 1015 over here. And similarly, if we add 455 with 1600, so we have 2055. So in down conversion, we are subtracting 455 from 560. So we have 105. And similarly subtracting 455 from 1600, so we have 1145. So the ease of manufacturing a local oscillator which can easily tune between 560 and 1600 kilohertz. So the ratio of maximum to minimum has to be small, right? So presently the ratio of maximum is 2055 kilohertz and the minimum is 1015. So 2055 divided by 1015, this yields 2 approximately. The ratio is 2. On the other hand, if we are using down conversion, so the maximum is 1145, and if we divide that by 105, right? So approximately we are having 11 as a ratio. So these two ratios determine how easily can we tune in to a particular station between 560 to 1600, right? So the lower the ratio, the easier it is to tune into a particular station, right? So hence we select this 2, and that is why up conversion is better than down conversion. Right, so in most cases you will just see up conversion, that is this local oscillator is omega C plus omega IF. So as this is our local oscillator. So in time domain, this mixer multiplies the incoming signal with the narrow band, that is the local oscillator at the receiver. So in time domain it is multiplied. In frequency domain we have a convolution, that is we have a convolution of the incoming AM signal with narrow band from the local oscillator, that is FC plus FIF. So basically this is the signal that we have received so far. Note that I have not discussed these two blocks so far. I will come back to them in a while, right? So we are right now in this section. So we received this AM spectra, that is the pass band, and then we are going to convolve it with this narrow band over here, and that convolution is over here. So that is we are trying to tune into 600, right? So our carrier frequency is 600, and we know that our intermediate frequency is 455. So if you add them together, so we have a plus 1055 and a minus 1055, and the cos function over here, this gives us two delta functions over here. So this delta function is at f minus 1055 and f plus 1055. Now the property of delta function states that if we are convolving this with this, so all of this would basically move to this delta function, and it would also move to this delta function. Let us visualize that translation. So at 1055, right? Say we are following the bold rather than the dotted line. So at 1055, now we have this point, right? So this station S1 is over here. That is, this is at 1055 plus 560 kilohertz, and similarly, and so on. But importantly, we also have these spectra in the negative frequencies, right? So particularly we are interested in tuning this S5 that is at 600 kilohertz, right? So what would happen to this minus 600? So if we add minus 600 with 1055, right? So 1055 minus 600 is basically 455, right? So if this is our 0, so at 455 we would have this steric 1 appearing over here, steric 1. That is, we would have this station with the spike. Similarly, following this dotted lines, now all of this spectrum would be shifted to the delta function, which is at delta of f plus 1055. So at minus 1055 kilohertz, we would have this 0. This part would be somewhere over here, that is minus 1055 plus 560, and in between we will have plus 570 and so on until we have the important station that we want to tune into, Tariq 2 over here. That is, we would have this one, that is 1055 plus 600. So this is actually minus 455. So we have a minus 455 and a plus 455, which is an intermediate frequency, and at this intermediate frequency we have tuned into the station S5. So hence eventually using a band pass filter over here at 455, we would be left with the original station, that is basically the one that we desire, and this is around 455 carrier frequency. So this means that at this band pass filter at intermediate frequency over here, we would be left with A plus M5 of t, that is the fifth station, and it is basically at cos omega if at intermediate frequency. right? And this just gives some kind of amplification to this signal. That is, we have tuned into a spectra which is like this, right? So this is our S5 of F, and then this is basically passed through an envelope detector, which is nothing but a diode. Then in parallel we have capacitor and a resistor, and then low pass filter, and afterwards we have a capacitor in series, and eventually we have another resistor, and at this point now we have M5 of T, which is then relayed to the speaker, right? So we have tuned into a particular station S5. So note that this dotted line over here, right? So this means that this oscillator is tunable. We can tune it to different frequency as well. That is, presently we have tuned to station at 600. We may tune to the station at 570, or we may tune to a station at 1600. But either ways, whatever the station is, by means of this tunable local oscillator, we can tune into a particular station. Now this brings us to the original question, that why do we have these two blocks in the first place? So these two blocks are there to reject image stations. And what are the image stations? So these are the stations which are basically located at Fc plus 2FIF. That is, at twice the intermediate frequency. If you add that with the carrier frequency, then that station is basically something that we call as an image station. So presently the image station for the station that we have tuned to, so we have tuned to a station at 600 kilohertz, right? So this is our FC. So what is the image station linked with this station? That image station is FC plus 2 times FIF, right? That is 600 plus 2 into 455, and this is nothing but 1510 kilohertz. This is our image station. So note that 1510 kilohertz is actually within the range of AM, that is from 560 to 1600 kilohertz. 1510 is within this. So what this means is, this station 1510, this would also come over here, right? So instead of just receiving this signal which was actually coming from here, right, now we also have this image station, and that image station is like this, and this image station would create interference, and this is undesirable. So in order to fix this kind of an issue which is dealing with the image station, we have these two blocks over here in the Superheterodyne AM receiver. The first is an RF filter, and then we have an amplification. So what does this RF filter do? So this RF filter is basically again a low pass or a band pass filter, which is basically having a much higher bandwidth, right? So we have a filter whose cutoff is before the image station, right? And so on the left side, so that all of these are basically rejected in the first place. over here in this block itself. If they are rejected at this point, so we would not have an image station at the intermediate frequency. That is the reason we have an RF filter initially and then we have a mixer. Also note that this is basically ganged up with the local oscillator. That is, whenever you rotate the knob of a receiver to tune into a particular frequency, you're basically not only changing the carrier frequency but also using a tunable band pass filter, which is over here. But this tunable band pass filter has a much higher bandwidth, and since it has a much higher bandwidth, so this quality factor is actually quite low, and we can create such filters. So this is basically the working of a Superheterodyne AM radio receiver.